Like it just dropped my internet connection. Whatever. All right, come on, Mac. You haven't really let me down much before. Okay, should we look at these results? It ran. First question: did it convert? In the case of factor analysis, but I think that's to be expected. We have thetas. Does everybody feel happy about the convergence?
Yeah.
These numbers look startling to you? Anything look crazy? I don't think so. Things look pretty normal. Okay, so it converged. Did it fit? Sounds like one of the units in my kid's preschool. Will it float? Which was also David Letterman, right? That was a big shtick he had for a while. So here is our posterior predictive model check for this. By the way, what I'm going to do for the posterior predictive model check, it's a little bit squirrely, but I wanted to be able to compare on the same metric we did CFA. I want to compare and contrast what happened with CFA. So the big issue with this that we didn't even talk about much in CFA is that should we really be using a Pearson correlation for these data? Pearson correlation is easy, but when you have a fixed number of categories for it, it's also potentially suffers from boundary issues and so forth. But we're going to do that. So what we're going to do is use the same, are you used to this syntax by now? Posterior predictive model check. We sample, we're going to save the correlation matrix. So we're going to generate from our posterior, we're going to generate a data set every step, every simulated value, every draw will have a data set, and we'll summarize that with correlation matrix, and we'll save all the correlations. And that'll be our posterior predictive correlation distribution. So with that, the analysis, this loop takes a little bit more time, and that's because it, to do the graded response, I've got extra loops inside of it per person per time. I probably could have found a way to speed it up. I didn't. Lisa, you look like I shouldn't have done it that way.
No, I'm questioning the rationale by which this is okay to do.
How so?
So you're doing the same process you did in CFA. You're trying to build a predicted covariance matrix, essentially, or
correlation
matrix, right? But the whole point of these data not being normal and continuous is that that isn't an adequate way of summarizing the relationship.
Agreed.
So who cares if it fits if the thing you're fitting to isn't the right answer?
Well, here's the problem. There's a whole the right answer is really easy to get in this case because correlation always works.
Right, but that's not. But
tell me the alternative.
Well, that's the whole thing is that if it's not multivariate normal data, then just knowing the correlation isn't knowing enough to be able to say that.
Well, correlation with multivariate normal is a little weird as well. It should be covariance, but yes.
That's what I'm trying to say.
Right.
The second, you need the higher order fit, right? You always talk about this.
You need to be able to look at whether it fits different moments. I agree. What would really be good is some type of categorical. The problem is twofold. Number one, we're sort of working a study on that part, right? I don't want to go there. But number two, to do like a polyquark.
Yeah, at least that.
Right? The polyquark. Do you want me to put the code in for the polyquark? Because you know what's going to happen through the simulation? It's going to break for some of the correlations, and I'll have to do some type of smoothing, and you'll see this weird catches because polyquarks are really uneven when it comes to simulated data. They're really messy. So alternative to that are things I don't want to mention because we're sort of working on it for research. But those are less messy, can be achieved pretty quickly, and can be done for every step here. Yes, I agree. The big flip of it then if you think about it, then how on earth would we compare it with the normal CFA? Because in the normal case, we're going to generate multivariate normal data, right? So we can't categorize that. We have to go and there's no way of putting, they're sort of apples and oranges, right? To take the normal case that's continuous, we're drawing from multivariate normal, we have this literally data that's not categorical. We can't do a polyquark on it. We couldn't do any other version of fit with categorical data that we'd want to do either, unless we categorize it. Well, if we categorize it, then we're not in the very normal anymore, right? So there's sort of this fundamental disconnect between categorical data and continuous data, and so we're basically going to acknowledge, yeah, that's a problem, and to the extent that the correlation is semi-accurate for these data, we will have an accurate fit measure. Does that help? Would you agree with that, at least I would say?
Well, so the reason you're not doing polychoric is because it would take too long and break for some of them.
It would break for quite a few of them, most likely.
Why?
What happens, so in some of our cases, with some of our B values and some of where our data were, we had small numbers of people in certain categories, and that will break the polychoric function for it. You'll have to smooth out what those categories should have for probability. I can show you, I actually started with this. I used the polychoric function from the psych package. And then I started doing this, and I would get, it was almost like 1 out of every 100 I would have an error of some sort. Because by chance, with 177 people, we're going to have, just think about it, we have 177 people, and we have this graded response where in our data, some items may have had 3 or 4 people pick a category response. And if we're randomly drawing this based on our model parameters that are fluctuating all over the place, it's going to be by chance, we're going to get a 0 there, or we're going to get a 1 there that's going to throw everything off. And the polychoric solver is going to just go, well, if I just sort of fudge these data a little bit, I'll get a number. Then I looked at the number, and the number is way different from what it should have been for all the correlations. But here's what I wanted to say. If I took the Pearson correlation of our data, here's Pearson, right? But if I did, the psych package is where I go here. Give me just a second to install it.
Are you going to show me they come out close?
I'm gonna try. I'm gonna look. I didn't compare them, but I'd like for them to come out close in a big picture sense.
Well, I don't mean to derail you.
No, you're not derailing, man. This, bless you. This is okay. Oops. Now there we go. 45 cells were adjusted for 0 values using the this is what's happening. And so let's take a look at some of these. Let's go with the first column, 0.66, 0.40, 0.61, 0.61, 0.60, 0.34, 0.57, 0.57. So yeah, typically we expect the polychoric to be towards the extremes. They are slightly. So, I don't know what we're going to do with this. In an ideal world, we'd be able to use polychoric, but it does take a lot longer to run. But there are other better measures. The question is, I can't get a polychoric for this process for CFA though. There's no way that multivariate normal, unless I truncate it to be categories, goes that way, and that's an artificial process as well. So does that help a little bit? All right. So I got this to run with correlation. Did anyone else have a problem with it, by the way? It's okay to have a problem with it. I like this. If I sounded angry about that, I'm sorry. I'm not trying to. You have a problem? Don't do dogma unless it's my dogma. Then it's not dogma. It's the law. No. I have a friend in grad school who, at the time, Judge Dredd was out, and he always said, "I am the law," like just quoting that. Never mind. It was Sylvester Stallone movie back in the day. Here's examining. Let's look at the number of correlations where we're off here, shall we? How many? First of all, before I show this, for those of you who didn't go and look at this already, how many? We had 13 misfitting ones in the last one. How many think misfit this time? How many say less than 13? One. How many say, sorry, I should say less than or equal to 13. Does that help?
I'll take less than that.
How about above?
It's tough to tell because I like that we're treating this as categorical data, but we saw a one-factor model didn't do well with CFA, and so you win some here, you can lose some there.
Exactly. Let's take a look. We have 10 misfitting ones. Slightly less. So this is what brings up the question: what are the differences between the two? Because I'm
I've seen
saying,
this in real data too, by the way.
what's that?
The fit gets better.
A little bit better.
A little bit better when you fit the right model.
Now, this is the same metric of fit. I've seen, like, when you flip over to the WLSMV in M+, and you get the RMSEA and all that, like, fit gets skyrockets. It's like, oh my god, fit's great, but there's issues with that. That's not really better fit, I don't think. I think this is a better metric, a more common way of looking at it. At least that's my bias. These are largely, if you go and look at the others, these are largely the same ones that are flagged. So let's do some comparison, shall we? This plot right here, you can rerun this code, but since I have the plot already, I'll just do it. This is the posterior correlation. Actually, no, I'm going to rerun this with this simulation, although I set the seed, so it shouldn't have been a big deal. Here we go. This is the mean of the posterior predicted correlation from the IRT model. So that if you look at this is all the data, all the correlations. Right here. This is the mean of the posterior predicted correlation for the CFA model. This line is where they're equal. So anything above this line, CFA is higher. Anything below this line, IRT is higher. And it appears the trend is a slightly higher under the CFA correlation. Somewhat interesting. This is the same IRT. This is the observed correlation percentile rank. Right? So this is where that observed correlation is. All the correlations we had. This is the one for the CFA. This is the line where they're equal. This says the percentile rank for most of the correlations in IRT are lower. So what this is telling me, although I should have plotted the posterior variance on here. What I should have looked at here was sort of the variance of these quantiles, but that would have taken a little bit longer. By looking at the percentile rank, though, leaning towards IRT for most of them, I think what we can say is the posterior predicted distribution of the correlation is slightly larger under IRT than in CFA. I think that makes some sense. Right, it's a categorical data model. Technically, there's less information in the data. Let's just see that. Is this interesting at all to you? Let's do some other differences. You want to see how the latent variable looks? There we go. Uh-oh. This is the EAP estimate for theta in the IRT version, the grand response. Here's the EAP estimate for theta, or the factor, in the CFA. Here's the line where they're equal. What do you see? This nonlinear relationship. Right? That's the coolness of the IRT coolness is sort of it makes the tails a little bit more nonlinear because of the way that the boundary gets enforced. But by and large, they're roughly the same. The correlation, it's not linear, it's a nonlinear relationship, so summarizing this as a correlation is not a good idea. But they're not far off in this case. I think that's somewhat interesting. Here's what I think is really fascinating, right? So in the CFA model, the way we've done our data, we should see that this is the posterior standard deviation for theta for IRT. So this is IRT's posterior standard deviation. This is CFA's. You see this line right here? The bulk of the CFA has close to one value with some weirdness up here, right? I went and looked at that point, by the way. That's a person who had 5s on all items but the first. So like a 2 on the first item and a bunch of 5s. Yeah. And so that sort of screwed up our algorithm. And I went and reran things with a little bit longer chain to see if it would stabilize, and I got the same result. But in CFA, because of the way the normal theory works, we can actually show, if we have the same data, we should get the same posterior standard deviation. So this is sort of an artifact of something in the chain that's going on with the priors. But what is this telling us? For most of the values, the posterior standard deviation for CFA, the IRT standard deviation here CFA here, so the IRT standard deviation is actually higher than the CFA one, right? Why is that? And that's what we would expect. We see more variation in standard deviation with IRT, but we should see it higher, and that's because IRT, by treating the data as categorical, we limit the amount of technical information we have in the item itself. Right? Information, when you take IRT and everybody's like, look, IRT is amazing. We can come up with an item of information, which, by the way, I asked you to think about. We'll talk about that shortly after this. Right? What they didn't tell you about that is if you had continuous data, you have a lot more information in the data because any very minute you can observe small changes in Y or the outcome that are meaningful that contribute to what you know about the trade. So CFA, if you look at item information for CFA, if it were true, it'd be way higher than our information curves for IRT. So I think that's sort of an interesting.
If it were true.
If it were true. So let's talk about information for a second. What is item information in IRT?
The precision of your estimate.
The item is how much information an item contributes to the trait. Or working backwards, if this were, I call it the posterior standard deviation theory of theta, we could also call this the conditional standard error of measurement. And if I can get my fingers working just right, this, by the way, is that person with that outlying variable. This is their posterior density for theta. And you see this really long tail here. And I changed the burn-in, I changed everything else, and I still get this long, it just it samples weird with it, what can I say? But if I can get this right, bless you. Let me do a plot real quick here. We're going to do the x-axis will be the mean theta. There we go. So this is our EAP estimate for theta, right here, from IRT. And this is our standard deviation, posterior standard deviation. So you would call this your conditional standard error of measurement in your traditional IRT course. Right? And you'll see that, yeah, there's some wiggle room right here, bless you. There's some wiggle room with where it goes. That's some sampling error. We could run a much longer chain and try to smooth that out a little bit. But by and large, it's fairly consistent, right? And so if you were to switch this, let's go back to the non-Bayesian version of IRT. Where does this thing come from? Where does the conditional standard error of measurement come from? I have a PhD. Sorry, that's, by the way, this is what happens whenever, some of our colleagues in previous defenses will start asking us questions that they should ask a student. PhD defense, I'm like, I have a PhD. You were going to say.
Can you clarify your question?
Where does the conditional standard error of measurement of theta come from in a non-Bayesian IRT?
Do you mean what contributes to it, or
What is,
like?
what's that? Oh, yeah, what's it equal to?
Some say my probability.
It's, how does it relate to, okay, I'll give you a hint where we're going with this.
How does it relate to information? Is that?
There we go. I've learned it as conditional standard error deviation of theta, error of theta is equal to 1 over the square root of test information. And that's where you start the foundation for item information, right? So let's talk about test information. I'll sit down. It's good to sit down. Should I put my feet up? Is that, I'm breaking every other norm here. When I got hired, they're like, we want you to change everything. And I'm like, what can I say? Fuck. Yes! Sorry. The information for theta, the test information function. If you estimate theta under maximum likelihood, right? And you think about maximum likelihood theory, then Fisher's information for theta and test information are identical. right? REL, you're the resident statistician here. Fisher information is. Never mind. Well, never mind. It's so.
You really are going to make me do that?
No, I'm just kidding. Here, let me go with my fuzzy stat version of it. All right. We would say as n goes to infinity, right? The distribution of the estimate of theta then would become normally distributed, and the variance of that thing would be 1 over the square root of the information. As a lower bound, assuming certain regularity conditions. Would that be roughly accurate to say? Right? But do you understand Fisher information? What I had to say all that, to get all there, I started with, if we started with maximum likelihood. Oh, shoot. We don't have maximum likelihood. We're sampling a posterior here. What's the Bayes analog?
Standard deviation of your posterior.
It is, exactly.
What's the fashion?
Huh?
Precision.
Precision, you could think of it that way. Can we use Fisher's information to do this? Can we use test information to do this?
Wouldn't you have like an information curve at every step of the chain or something?
But every step of the chain is not a maximum. And that's the problem. Every value in the chain is not guaranteed to give you the MLE for theta because you're going to sample theta as well.
Yeah, I got stuck on that part.
That's what I'm saying.
So you have an information curve, but then you have like some sort of window around it, right? Like.
There's no information. Well, you could compute the
You can
under ML information curve from it. But I'm not clear. I'll just put this as the limit of my knowledge. I'm not clear that you meet the regularity conditions for that to be the case because you're not at the peak of the distribution.
But if you take your best estimate of the mean of your posterior or whatever, or your measure of central tendency of choice of your posterior, and treat that as like known, you can compute information from it.
You could, but that would not necessarily be the mean of what's happened. I don't believe that's the mean, is what I'm getting to. So let me go with what I would say. And I tried to look this up, and I didn't find this in any of the IRT books. There's probably papers out there. I didn't do a very thorough search. But let me do it this way. Ben, I think what you said was right? What we could say is, for theta, what we know is the following. We could figure out the EAP is the expected value of theta given our data, right? And then there's a function for that. Right? What is that? Oh gosh, here we go. Oh, it's too high up there. There's an infinity up there of theta, right? Times. Well, what's our expected value for what is our posterior distribution of theta? Ooh, that's a mess, right? How about we just call it f of theta given x, right? But that is Bayes' theorem, right? D theta, right? So this thing really is. I shouldn't do this because I'm going to screw this up too. It's equal to f of x given theta, f of theta, and then in the denominator we marginalize across. This is theta and x. We marginalize across the f of x right here, right? Something along those lines. All right. So in theory, we could come up with what the posterior distribution should be. It's really tough. It's a tough interval, right? And similarly, we could say that the standard deviation, or the expected variance of theta given x, is really equal to the expectation of theta minus the expectation of theta squared, right? Squared, that thing, using a similar process. But what I'm trying to say is I think there's probably a relation to what you're saying, but I don't have the automatic nature of my mind saying it's possible to do it, to derive it. So. But this has ramifications.
It would be some sort of approximation.
You could take, I think you would define that, and I think in the limit, this will become Fisher's information as n goes to infinity, or in our case, as the number of items go to infinity for each person, right? So we could use that as a limiting theorem, but it's probably going to be larger, right? I think the observed is going to be larger. So why I'm saying this is if you think about To me, this is the complexity is fun. That's because I have a PH now. Right? That PH is like, oh, I can think about things that are interesting to me. How would that work, right? Think of it this way. If we didn't have test information guaranteed, what's item information then? What's a good item? That's hard to think about, right? Yes, maybe we could I think we could approximate it.
I think you still have it, it's just that it's not one number.
Right, yeah, right,
it
exactly.
You have wiggle.
Oh yeah, definitely you have wiggle. And if we could compute an item information at every step of the chain if we wanted to. We could even compute for a given set of theta as a test information. And again, assuming certain asymptotic properties, those would become true. Because Bayes and the limit of Bayes when n goes big, in our case for theta it's when the number of items gets big, we get the same result. So it'd be an approximation, it'd probably be an approximation with smaller variance than should really be there, but that's fine. Certainly solves the problem with the integral that we have, right? Right?
Integrals are the worst.
So it's actually a multiple integral because of the integral across theta, but then in Bayes' theorem we actually have an integral in there as well, so it's a nightmare. So what do you think? Is it crazy? Don't do Bayes is what you're thinking.
So,
Yeah.
in non-Bayesian framework, we usually to get test information, we only need item parameters.
Right.
But here you mean we should not using item parameters.
You-
we should not get.
If you do the test information here, we could still do the same feature here. There's nothing that stops us. We have item parameters, and in fact, we have them at every step of the chain. So we could even come up with a posterior distribution of test information if we wanted to.
That's what I'm trying to say.
Right.
Is wiggle.
Right. But that's test information. To get test information relies upon asymptotic theory under maximum likelihood that we don't have in our process.
And then it's similar to the issue that we have before trying to look at the goodness of fit indices.
That's right.
You're getting the same messy area.
That's right. We are in a very messy area. Like if I had to do this today, my first thing would be exactly what Lisa was saying. I would compute item or test information at each step of the chain because I could. I would acknowledge that that's imprecise and that subject to theta having enough data, it's likely to have a smaller variance, or whatever. But what I wanted to get you thinking about was that's an ML result, right? It's kind of an odd thing when you sit and think about it because it's a foundational result in what we do in a lot of IRT in the world, and yet it's easily gotten to in our case. Frown for.
Okay, so forgetting the whole Bayes is the way of the world thing. If you're just doing Bayes because it gives you numbers, right?
Mhm.
So if you pick uninformative priors
Mhm.
and you're using the same likelihood, then in theory, if I go run Parscale or whatever, I should get the same point estimates for my A's and B's
Yes.
and EAPs and whatnot.
Yes. And
So if I'm getting the same answer, then why can't I use that same and make my test information curve the
it
same
should
way?
be roughly the same. I'm just saying the theory part of it, where it's founded on, is not the same. The
And I'm gonna quote you, yeah, fuck that.
Well, no. I'm going to say that it's likely as n goes, or as the number of items in our case, we're talking about theta, as the number of items goes to infinity. Yes.
Well,
The question is, where's infinity?
because we know that to be true, right?
It's also
Because-
true in the ML case. You're right.
Yeah.
But the other part of what I'm saying this for is, like at the end of the chain, yes. I think the other part I'm struggling with is within each chain iteration as well.
Yeah, well, don't do it in the chain, then just get your A's and
EAP.
B's out and then do it at
With
the
the
end.
EAP estimates, yes, I could actually do that. Absolutely. I think we pretty much argue that our priors are uninformative enough to let that happen. So, and that process, by the way, has been happening. If you look at like Bilog or even Parscale, like they have priors. I don't know about Parscale, but Bilog had a default priors for some of the parameters for C if you did a 3PL that people would still go and take numbers and do this with. So, Just wanted to bring that up, though. One of the key results in IRT comes from ML. I guess technically speaking, if in our chain we were sampling A and B, and we were imputing for each person their MLE of theta instead of sampling theta, that would probably be a little bit more accurate. But whatever. It's probably going to be roughly the same. Anyway, has this class just fallen off the rails completely?
What I've been finding a lot with Bayesian analysis is that in a lot of situations, it can help you get estimates for your parameters that are difficult or impossible to get under a lot of MLE cases. But once you have your estimates, some of the later things you want to do, like information, like figuring out what uncertainty is.
Right.
MLE does really well for you because it's built into the asymptotic theory and you've got all that. But here it gets a lot weirder.
Right.
So there's definitely some trade-offs in Bayesian analysis, it seems.
I will tell myself for what I'm going to say later. I will sit in a corner and think about this. but at the same time, don't get me wrong, uncertainty is important, but how many people really look the uncertainty of some of the things that we are worried about uncertainty?
Well, how many people do or how many people should?
Well, how many people actually do?
Yeah.
Very few, but a lot of them should.
But I will say this, a couple things. If you're out to give somebody a conditional standard error of measurement for theta, there's your estimate right there. Whether or not that's equal to test information is irrelevant.
Right.
It's there. It's when you want to build an adaptive algorithm and you have a Bayesian system building into it, it may be a little harder. But if we're off in adaptation for figuring out what's the best item to give someone based on like maximum information, does that really matter? Probably not there. We're going to be off a little bit by picking theta. We're going to be slightly inefficient. Is it going to be, what's the number of items more inefficient? I don't think it justifies the multiple integrals I have to solve to figure this out or numerically integrate over. So I agree with you. I think in the big picture, like if you're going to go do Bayes in the day-to-day, if your job is to do Bayes in IRT in the real world because people need scores or you're trying to quantify kind of ranges of standard errors based on, and to put in the technical manual, which by the way, I wish we would report score reports, but just leave that there. This works just fine, or the approximation by normal and the whatever will work just as fine. But yeah, the bigger thing that I worry about is I love the thought of building a Bayesian, a fully from start to finish Bayesian system for a lot of what we do in assessment. There's reasons for that I think are really practical. One of the stumbling points for me is this: like, how do I, if I wanted to build an adaptive algorithm for it? Well, yeah, I would totally do the information that comes out of maximum likelihood because it's doable quickly. And doable beats not doable, right? Most of the time. I guess I'm going to hate myself for saying that. Anyway, what do you think? Anyways, one of those things I'm trying to give you things to ponder. Not trying to ruin your Friday. Both of the professors over here look very unhappy with this result. I have just squandered any goodwill left. I came in just barely 3.5 months ago, and now I've already found myself alone and bitter. Emotionally and intellectually isolated, because I took sacred ground and dug it up.
That sounds like the start of an adventure book.
It does.
Well, like Newton was famously antisocial, right?
Ah, yes.
So
I'm just famously anti-establishment. I think that's
That's not like I'm the champion of adding shit up.
I know,
We
no.
don't disagree about
No, I know. Ariel took exception with sums of squares, and you're taking exceptions with information. All right, should we do partial credit? Let's move on. The last couple models are just how to do them. I'm not going to deep dive into it, so we'll just be able to see the syntax and move on. I'm not going to give you this, well, that last homework where I sort of said, this might show up in the homework, may not. We'll figure out an article that looks nice and try to replicate it. Sound good? I think this is the generalized partial credit model. That's what I'm going to try to estimate. Would you like to describe this for me? Can you come up here and describe this for me? Because I'm terrible at partial credit. I really am.
Well, I don't like that you use B, because the B doesn't mean the same thing that it used to. This is not item difficulty. This is the point on data at which the next category becomes more likely, not necessarily 50%. So B is tied to 50% for me, that this is not.
Gotcha.
Yeah.
Sorry. I
So-
wanted to keep it consistent.
So the model has these thresholds, meaning 1 versus 2, 2 versus 3, 3 versus 4, 4 versus 5, as opposed to 1 versus something else. 1, 2 versus something else. That's the graded response.
Thank you.
I do measure.
Did you ever have a grant that did like an adaptive test?
Well, you wrote the algorithm, but yeah.
Well, that's actually what we heard about this, is we use Bayes to do the algorithm.
Yeah.
But what did you make it adaptive on?
Attention.
Response time, or display time.
Yeah.
That was awesome. You can vary item difficulty by how long the person has to respond. Think about that. Is that crazy or what?
That's pretty cool.
Yeah, anyway, sorry. That's just, I thought I'd say that because it's relevant here. But, you know. I love creativity. This is just part of it. Okay, so in this model, what do we have to do that's different? Again, you'll note the dcat is the same in the syntax. We just have to change the way that we generate the probabilities to make this work. The generation system here, I start with the interior of the kernel, and then I sum that up, and then I take the E of it, and then I finally create that final probability, and you'll see this outer sum. This works out to be where that needs to be overall. So if I go through this syntax, go through here, actually I think this is just show my results rather than, no, it doesn't show my results. Oh, all right, we'll let it run. Let's do some talking. Okay, analysis is running. So, any questions for me about what you've learned so far? Anything that you'd like to complain about?
I like R2 jags better than just R jags.
Oh, this has gone much smoother, hasn't it?
Yeah, I
Can
agree.
if we use adaptation in the model syntax, then can it reduce estimation time?
If we use adaptation, it can. It could. Yeah, like in the JAGs, if we were to ask it. In theory, yes. Maybe I should have put that in there. I don't know. Does JAGs have an adaptation? So, just to back up everyone, what adaptation tries to tune the Metropolis algorithm to make it more efficient. So yeah, in theory, it should do that. I think by default, let me double check.
Because it really takes some time. For 10 replication, it took me like 2 weeks using HPC.
Yeah, I can believe that. 2 weeks for 10 replications? Yeah, that's tough. I don't believe in R to JAGs we have the option to help adapt. So this is where I think we'd have to go back to JAGs itself. I think by default when it calls JAGs, it will use JAGs like 1,000 iteration adaptation, which is sort of an arbitrary default. If you think about all the types of algorithms in the world, depending on model complexity, you may need more or less of that. I think this, you bring up an interesting point. So the model that you're running that took 10 iterations took 2 weeks, right? On the HPC, a high performance computer.
It's actually it is
Mhm.
but still for results it took me 5 days.
Yeah, I can believe that.
For HPC, 5 days.
Yeah, it is. At that point, it's almost where you need to. If you think of how many times you're going to run that, is it going to save you time to write it yourself? Which, by the way, what I taught you about Metropolis you can do with a Metropolis algorithm. A lot of times what happens, because JAGS is so general, it slows it down. You can write much more efficient code to do a very specific algorithm. And actually forget about multi-level, forget about Metropolis for multi-level, like the Jean-Paul Fox book, the 2010 book, has a multi-level IRT, and he talks about how to do it with Gibbs in that book. So you could even do it even faster, but I don't know that JAGS is doing Gibbs, and I think that would be.
So the problem is not really similar to the existing software like the number of iteration.
Yeah. It's a lot. So let's take a look and see if this worked. Here's our convergence for A's and for B's. Ta-da. Everybody feel happy about convergence? One of the things that we can talk about with this model is whether or not there are reversals in the order of B. And so here's item 1's B2, B3, B4, and B5. They go in order. I think I saw a reversal in item 10 here, though. Item 10's B2 is 1.665, and then 1.258, then 3.558, and then negative 8.41. And so the question then becomes, which is better? Is the partial credit model better, or is the greater response model? Let's take a look at DIC to compare them. You'll note I didn't use DIC to compare the factor analysis and the greater response model. I'm not clear whether or not you can or can't do that, mainly because the scale of the likelihoods are different. But if we go back through the BIC real quick, what we can see is, or the DIC, excuse me, we have 3160.1 shows up for here. If we look at the greater response, it's 3093.5, which indicates the greater response is slightly preferred, right? It was 3160 before. You want to see what it looks like in CFA? $4535.7. But that could be because the normal distribution can get very peaked when the variance is small. And it's on a different metric than probabilities in a probability mass function. So
I don't see how that's comparable.
I don't think it is. But because we use dcat, or the same distribution of the data function, the same probability mass function for greater response and for partial credit, those are comparable, right? Questions, thoughts, comments? Are you enjoying this?
So I have a question.
Yeah.
In maximum likelihood, literature usually say that graded response and partial credits, they generally give like comparable model in maximum likelihood framework. So like they argue that usually it depends on how you conceptual, like the order of the scale you believe. So it's more like a conceptualization of the model instead of the model comparison.
I can see that. Yeah, I think you could see that, like the partial credit sort of greater response is one version of partial credit you could think about with the order constraints in. It's not exactly the same, but I could definitely see them being roughly the same, mainly because the multinomial distribution is the same, and we're talking about minute differences in one of the parameters. There's not a lot that can be different, I think, between them. So that's a good point. What do you like better? Partial credit or greater response? Who likes partial credit better? Who likes greater response better?
Greater response there runs clean.
That's it. That's what I think. It's a quick one.
But there's that assumption.
Yeah, it's a tough assumption to come by. All right, finally, I realized I didn't make my syntax for the nominal. I mean, I made my syntax, but I didn't make my slide for nominal response. But nominal response is a model, and I might be able to draw this real quick. The nominal response model, come on, pencil, there we go. What we're looking at here says the probability that x is equal to some category given theta is equal to E of A for the, and this is person and item category. For the item, A for the item and category times theta for the person minus B for the item and category, like this. And then it's over the sum of the term in the top. So it's a divide, what we call a divide by total model. Like that. And this is across all the categories for an item. This is like a big C up here, that item. Right? There are some issues with this model in that we have to, I was reading a Thyssen paper before I put the code together. It's what we call doubly not identified. We have to make constraints not, so what this is saying is that every category gets effectively an A and a B. But we have to make a constraint on A to make it work, and we have to make a constraint on B to make it work. You can't actually estimate that, every A and B by itself. So typically, if you read, like going back to Darrell Bach, 1970, 72, I can't remember, 70? 72. 70, I think it is. Anyway, he liked to say IC equals the sum of BIC equals 0. So there's a sum to 0 constraint across the, this is across the categories, right, for it. Or if you do this in M+, data R, data is nominal. Sorry.
You can say that.
Oh, pick your preposition.
Nominal is.
Yeah. Oh, nominal is nominal R. Sorry, it's been a while since I did M+. Then M+ enforces the opposite to this, where you can say pick one A and pick one B and set both of those to 0, right? And was it the last category they do?
Last part is the reference.
So it basically says the A and the B for the last category get set to 0. And what that ends up doing, if A and B are both 0, this last category has an e to the 0 in the numerator, which becomes a 1. But the probability gets re-expressed because of this sum to 0 in the bottom. So just because it's set to 0 doesn't mean it works that way. So there's other ways of coding this that are out there. I'm going to take the pure, no, I'm just kidding. Take the original way, the original bot coding, because for whatever reason I found that to be really convenient for my own head. And to do that, the code's getting a little bit, believe it or not, the code looks a little nicer, doesn't it? Right? Here, again, the data are still dcat, right? That sort of one trial multinomial. CNUM is the numerator, and so I have A times theta minus B at the top, right here. And the probability below is, actually it's E raised to the power of A times theta minus B at the top. And then finally, the probability for each item and category is that number divided by the sum across all categories for it. Again, I'm going to identify theta with a normal 0, 1. And again, here is where I am taking B, the last category. The last category is B. Oh my goodness. It should be -1 times the sum of all the others. So they sum to 0. This, by the way, did run as a constraint. But there. So basically, it's this -1 times the sum of all the other B's for it. I just picked the last category for the heck of it. You could pick whatever category you like, though, which is the nice thing about this. And once again, to make this work, although I needed to show this for you for the previous. When we're done with this, I'm going to go back to partial credit, because I want to show you the initialization needs to be a certain way. But here, the initialization, we're going to have this Model 3 init do this for us. And if we were to just call that function, you'll see that here the last, because we're fixing the last categories, A and B, we had to put an NA on the initial values in that code. And that code to make that do that is this, where I'm saying A becomes a matrix where we're replicating values for this. So I'm replicating random uniforms for the first 4 and then putting NAs in the last. Everybody okay with that? Cool. By the way, the partial credit version of that, the very first B had to be 0. And so it was the flip. I put the NA at the beginning, not the end. That's the one catch. So now, let's get this thing fired up. I only ran it a short amount of time because I was trying to make it go quicker. But we'll just see this and we'll call it good. So, anything else?
Why don't you ask Jihan about the example he built for my class with the nominal response and the partial credit?
Oh, I just think I would, but you just did for me.
Want to share with the group what you did?
So in that case, the kind of there is one category would be something like not applicable, and the other could be the other category is ordered. So in that situation, the other part should. So we fit a nominal model and constrain the ordered part within similar to the greater response.
Partial credit.
Partial credit.
So think of it this way. If you have item response where you've got a bunch of nominal, I like it with nominal, but partial credit. You could have ordered responses, then NA, like a non-response. You could model responses in another type of category. And if you think about it with nominal, right? Like, what's your favorite ice cream? Strawberry, vanilla, chocolate, I don't know, pistachio. And then someone looks at it and says, I don't like those ones. Like, where's my butter pecan? They don't respond. A non-response is another category of response. Right? So rather than just impute what that response would have been, why don't you just model it? So you can think about that with nominal, but then you can go on and do that with combinations of, there's an over-the-top nominal where it's effectively non-response versus an ordered category. And that's what that is. This is a paper by Corinne Huggins Manley, came out when?
2017.
Was it in SEM? Anyway, I remember notably in that personal communication on my birthday.
Yep.
She invited me to give a talk at Thera. It was on my 40th birthday, and it's my birthday. Anyway.
Oh, that is good.
What you're going to see here, folks, is problems, right? Look at that. Convergence is a real problem here.
Because you didn't run it long enough, or because it's too hard to model?
It's a hard model to make work. Look at my variances, they're 1. And I'm not ruling out there may be some other issue with my model or my syntax, but that doesn't look good, does it? If I were to you can't really see it until I get all the way through, but take a look at that. We got multimodality in the A's, which makes me think I didn't get one of my constraints just right. You want me to try one more time? There's another way I can identify this. Why don't we just make the last category 0? Try that. Give me just a moment here. Uh-oh. Nope. Don't run. Oh no. Oh, R. You're killing me. Yeah, of course. Yes, there's an error there. Can you run my chunk though? Would that be okay? Nope. Alright. Well, maybe this is not meant to be. Actually, I still have a little bit of time. You want me to try rerunning it? Give me a second. I'm gonna tell R who's boss though. I don't like to feel like I'm boss of anything but my computer. What's that, Aria?
I was going to be like, oh, I already start defending some of the square. I want to start defending
All these hills we're dying on here. There we go.
It may be a sign that I'm getting way too old.
No, you're fine. It's okay. I defend, what do I defend that's old? I don't know. I try to move with the times. Now I can't even listen to new music. It's terrible.
New music, what do you
I know. I used to joke about it. Like, turn the page already. I used to say that, right? And now I'm like, I turn the radio. I'm like, oh my god, I am officially old. It took me till about like my late 30s, but
Yeah, when I was young, I couldn't understand how people get stuck in older music.
yeah, 80s music. That was too much for me. Yeah. And yet I'd still willingly listen to like Led Zeppelin. So, yeah. Yeah, I went to a concert last Friday in Chicago. But it was by a band that's kind of old now. It's Muse, and the band that opened for them was Walk the Moon. They're 18 or 19. And they're like, we're just like you guys. The lead singer, we're just like you guys. We love these guys ever since we were kids. And I'm like, yeah, that wasn't me. Because 18 to 19 years ago, Muse was, coming out and I was in the UK, was trying to do things. Anyway, so I was like, yeah, that's nice. But yeah, it was an absurd concert. It was awesome, but it was sort of I think they'd say fantastical. It was like Electric Light Parade meets or robot zombie apocalypse. It was pretty ridiculous. Yeah. Big fan. I've always loved, ever since I can remember this. I was trying to write my PhD. Sorry, never mind. I guess that's not my story. You'll have to hear this later. It's all right. You're gonna have to live with the faded, but again, look at that. It's not working. So, if you want to see some non-convergence, there you go. There's some multimodality for you, right? Yeah. So there's something else in the identification that's screwed up here. That's what's telling me. So.
When did I report that in the paper like that? It's something identification that is.
Yeah, I screwed up identification. No, in fact, I've always found it like really shameful. Like if I were to publish a paper and someone came along and said, "That's not identified," oh, that's bad. That's sort of like ha ha, I got you. It's like touche, right? I remember I worked in grad school for a guy named Bill Stout, who was instrumental in my career. He published, I want to say it's a book chapter, or maybe it was an article with another couple people, called The Unified Model. It's a diagnostic model. It had like everything in it. It even had like a spot for an elephant in a parade and all this sort of stuff. It's crazy, right? It had enough parameters to, I don't know, build a bridge around the world twice. And this model, they realized, they started trying to estimate it. So they came up with the reparameterized unified model. And it still had a term in there that was like, so then they came up with the reduced reparameterized unified model. So it just keeps going and going and going. But the irony was, when you start doing this with Bayes, all of your model problems are sort of laid bare whenever you see stuff like this happen, right? It's notable to me that this one and sort of this one, although they're not exactly reflected about zero. So there's something, this should just be the data set for this. I don't know.
This looks like a drawing Huey would make.
Maybe we should print this out and put it in this room.
But when you can identify your model is having problems because a particular parameter, will it be fair to fix that parameter?
You could, yeah. Yeah, there's nothing wrong with it.
Is acceptable?
Yeah, it is. It's just there may be bigger issues. Identification's a tough thing because there's certain statistical things you need to know, and I think this is statistically identified, but there's something else going on that I'm not seeing what's causing the problem. And actually, you know what I think that might be? Oh no, I'm allowing A and B to be fully normal, be estimated freely. So that's what they're supposed to be. There's no bound on A on this. It should be whatever. Okay. So if I'm going to be like Rosh, there's problems with the data, not the model. The other thing I was going to say, sorry, I'm trying to get out of my trace plot without the mistake I made last time, was that like non-identifiability could be something with your model parameterization, but then you could also have that with data as well. And tracing down why that's the case is just can be very, very difficult to do. I wonder what would happen if I last attempt here, everybody. We'll just make the first category 0 for each of these items, because that's the one with most of the data. These are really heavily skewed to the right. By the way, this is another trying to oh, that's right. I need my input data now has to be different. So I need to put the NA at the beginning, not the end, which of course, again, made me question my love for this class. Not that I don't love you guys. You being everyone in here, the students. Although I will say there's a favorite. I have a favorite, but you know.
I'm sure you were talking about me.
I pointed just generally. Somewhere over there.
It's the accent.
Oh yes, attempt to find. No. Yeah, I'm not seeing where I'm getting this error from. Let's see if I try this again. Anyway, if this doesn't work, we're out of here. Oh, there we go. Nope.
Okay, we're out of here.
We're out of here.
It's 5 minutes.
It is. Nope, I'm done. You want to play with this if you like yourself. We'll call it good. Let's see here. Homework 4 due next week. Online and icon, you can see your grade up to the minute. You'll see a 0 for homework 4, a 0 for homework 5. That just means you know when you can quit. If you want it. You got the grade that you want, you can quit. But my goal is to make sure all of you not only pass, but get A's or even A pluses.
Once I do the memes.
Oh, that's right. If you bring in a Bayes meme, I will give you extra credit. Preferably one you make yourself.
Does this university do A pluses?
I heard they do.
Yes. Okay, good.
I'm
Okay, you
assuming for grad school, but
What's that?
I definitely know for undergrad.
Okay.
It's weird to me, but
Take classes? Yeah, they classes.
I'd like you all to be A plus.
I never give an A dog. I just say
I know.
You know the only so I have this. There's a story I have about this in grad school. I got 1 A plus in grad school is when I was working for a professor. So my friend Bob got an A plus in math stat in the last semester of math stat, and he was just he was amazing, right? He was great at it, and I was like, oh my goodness, hats off. And that same semester, I got an A plus in the ANOVA class that was the vector version, the projection, the Chaffee version of ANOVA. And I only got that because I was working for the professor, but and so like we compare these, like, look, I got an A plus. He would always say, look, I got an A plus in math stat. I was like, yeah, and I got one in ANOVA. Look at that. Really, you could do the math stat, but can you do ANOVA with projections? I don't think so. And it was only because I worked for the dude. So, all right, everybody, have a great afternoon. Have a great week.